Hi and welcome to my talk about our ground support equipment Phasemeter. We are currently developing Phasemeters in collaboration with the flight hardware. They should be usable for technology development, to have a Phasemeter in the lab for testing and assembly and simulation of the flight hardware. I am Darsow-Fromm and my part is currently about phase noise component measurements and about the software part of the Phasemeter. So that is what I will talk about today. Here you can see a small overview of our Phasemeter concept. It is based on the MicroTCA 4.1 standard. And here you can see such a crate where it lives in. It's really modular and flexible, and we have here many different slots that can be used for computers, FPGA and so on. So we will use 8 FPGAs for analog input. So, and here on the back side the analog input channels will be connected, or the analog digital converters with 8 channels each. And there will also be a digital output with a DESY card on the back side to log lasers, and here a frequency distribution module to provide the pilot tone. If you want a deeper overview of the whole setup, then consider Oliver Gerberding's talk about that. My talk is mainly split into 2 parts. So first part is about a Python kilohertz Phasemeter, which I've used for component testing and to set up the whole crate and the hardware and all the interfaces. And then a second smaller part is about Megahertz PLL, so the next step towards the real Phasemeter which should be implemented. And that we will use for ADC testing of the final ADC cards. So this image here is the Z-7000. That's our FPGA which we use. And here is an ADC card, which is currently an FMC 116 card, but will be replaced to our real ADC front-end card. Then this is the FPGA part, where here in this implementation only a CIC filter is used to decimate the data down from 80 megahertz to around 40 kilohertz. So the Phasemeter is mainly living here in the ARM chip and running in Python. And yeah, I said we used that for component phase noise measurements. So that is mainly about components which we use in the ADC or the pilot tone distribution. This is the setup for most of the components. Sometimes it needed to be a bit more complicated depending on the component which we tested. So here the Z-7000, which gives a clock reference, and using 2 signal generators, we are able to have testing frequencies between 5 megahertz and 2.4 gigahertz. That is split here and into one reference line and one line which goes through the device under test. And the second signal generator runs with a small offset, so the local oscillator of nearly 10 kilohertz, which is here mixed and low pass filtered. So in those parts we both will have signals of nearly 10 kilohertz, one with the phase noise of the device under test and one with the reference. So that was the setup to measure at megahertz with a slow data acquisition. Here you can see an example measurement. So the dotted lines are 0 measurements of 5 to 75 megahertz. And those are one of the components. So this one is an amplifier, which I've measured here. And you see all curves are well below the LISA 1 picomент requirement. And that accounted for most of the components. So nearly every component which we measured was good enough or at the edge of being good enough. But for some components, the temperature coupling is really significant. So depending on what happened to the room temperature during the measurement time, it increases here in this part. And for some components, this coupling is critically high, for some a bit less. One other important measurement is about our RF backplane. You already saw it in one of the first pictures. So this here is the RF backplane. It is mainly used for the distribution of the 75 megahertz pilot tone. So here will the clock module sit, which distributes all the frequencies, and those are here connected. Here you can see the schematics. They will be connected here and go to the individual slots with the different cards. To have a high enough phase stability, the stability between all those channels needs to be high enough. So the drawback of this current implementation of the RF backplane is that the lines here have different length, and we can see that in terms of temperature coupling, which is here visible on the next slide. So here you can see a zero measurement of the backplane. So here I've tested two lines with equal length. And the green line here is the shortest line against the longest line. So slot 4 versus slot 12. And that doesn't meet the requirement here, but I have to remark that was not in controlled temperature conditions. So maybe it will be good enough if I can move the setup to the lab as soon as the temperature stabilization is working there. And this RF backplane is directly in the airstream of the ventilators and the crate, so it's just not possible to do a passive temperature isolation there in this position. Yeah, so if it doesn't get good enough, we have to redesign the RF backplane to have equal line length. Let's continue with our Megahertz PLL. So here you can see the scheme, so the small overview. We have still our data acquisition card, and here on the FPGA is now a bigger part. So I've implemented 80 megahertz PLL, then a CIC filter for decimation, and now Python is only used to get all those data and write it to a file. So that PLL we will use to test the ADC front-end performance. Yeah, it's still just the next project to get a step further towards the Phasemeter and to improve all the infrastructure which we've built around that. Let's have a look on the zero measurement here. Note that it's currently running with 32-bit, so therefore you can see this relatively high noise at higher frequencies, and the overall noise floor should go down if I increase the bit rate. You can see here at least the difference between channel 1 and 2 is mainly below the LISA requirement, and that with the FMC 116 ADC card. So the final hardware will get better, but we are already close to the performance. So let's sum up. We have our Python kilohertz Phasemeter, which runs as a prototype, and we measured most of our critical components. And while developing that, we build up all the interfaces between FPGA, ARM, PCI Express. We have a running Linux distribution on that, and so there was a bunch of side developing while doing this kilohertz Phasemeter. So the current thing is the Megahertz PLL, which should be used to test the ADC front end. And it is further used to improve our infrastructure and to get more steps towards the real Phasemeter. And in the next time, we will improve all our setup, and finally some hardware will get ready. And we are collaborating with the AEI in Hanover to integrate the algorithms of the flight hardware in our system, and yeah, to work together on that. So yeah, thank you for watching, and get in contact if you once need Phasemeters for the lab. Thank you.